We just finished the problem that was asking for the final velocity after this inelastic collision between two clay objects. And we went through using the conservation momentum, found that the final velocity was 7.24 meters per second at 17.3 degrees. So in this last problem, I had calculated the initial momentums of both objects in the x and y up here, so you can look at the last video to see how I did that, or just look at the work. Pause and look at the work to see how I got those. I just copied them down below just so that they're easier to reference instead of scrolling our screen. Okay, so the second question that we are answering here in this video is, what is the change in momentum for both objects? And we are going to use this place down here. Oopsies. I will just put a line to show that we are starting new. So we want to find the change in momentum, otherwise known as the impulse. So before we get started on this, right, we're thinking we still have to be talking about x versus y. And it's important to have that information because we're working in components and we need to be thinking about the x direction independent of the y direction. So when we're dealing with the change in momentum, right, delta p is equal to mass times Vf minus V naught, right, delta V. So again, specifically, we're going to be talking about the x final and the x initial, or, right, delta Py mass Vfy minus V naught y. So we're still keeping this idea of components, okay? So with that, over here, right, we can see the pink is x, so this 9.4 is the initial velocity in the y direction of the first object, and the negative 3.42 is the initial velocity in the y direction for the first object. So I have the components of the initial velocity, but I do not have the components of the final velocity. So that's going to be the first thing that I do, because in order to answer this question, we need the initial and final velocity in their components. So we have a 7.24 meters per second, and we're going to have some x velocity, we're going to have some y velocity. We know the angle is 17.3 degrees, so we can go ahead and break this into its components. So I'm going to do the cosine of 7.24, 17.3 times 7.24, so we get the x component velocity is 6.91, and 17.3, we'll do sine times 7.24. This gives us 2.15 meters per second. Now remember, this is the final velocity for that whole object, and both mass 1 and mass 2 are encompassed in this object. So you're going to see that the final velocities in the x and y direction are going to be similar, but it's the masses that we are going to multiply that are going to get different. So we're interested in both objects. So I'm going to say for object 1, it's going to have an x and y momentum change, and the same thing is going to happen for object 2, x and y. Okay, so let's focus on object 1 first. We're going to have the change in momentum of 1 is equal to the mass of 1, and this is x, right, specifically because it's in that pink. Mass doesn't have a vector to it. Vfx1 minus V naught x1. Okay, right, because we're interested in this first object's x information, the final x information and the initial x information of the first object. So delta P1x, the mass was 5 kilograms. Vfx, remember this, 6.91, minus the initial velocity, right, was encompassed here in the initial momentum of the 9.4. Okay, so we have 6.91 minus 9.4 times 5. So I get a delta P1x of negative 12.45 Newton seconds. y is going to be similar. P delta P1y is equal to mass 1 VFY1 minus V naught Y1. And plug in delta P1y is 5. Oops. The y final velocity is 2.15. And the initial one here we see is, right, minus a negative, which means plus 3.42. Okay, 2.15. We get a change in momentum of the y for the first object is a positive 27.85, right? Because it was going downward, right? The first object was going down in the y direction, and then after the collision it is going up and to the right, so we have to have a positive change in its momentum. So if we come along and we put these two components together, we're going negative 12.45. The negative is taken care of by a left arrow, 12.45 Newton seconds. This is going up 27.85. And then...
Sorry, I was yelling.
Oh, you're... Say hi to my kids, Mr. Willie.
Which kids?
Physics honors.
Oh. Why was that?
Video. You can say hi. I'm making a video for them. You don't want to say hi?
Hi!
Okay, there we go. Thank you, Mr. Willie. Put these together. And take the square root. Get 30.5 Newton seconds. And again, we need to find the angle because it is a vector. Let's see, 27.85. I'm using tangent again, and we're using the inverse of it. And this is 65.9 degrees. Okay, so the impulse, or the change in momentum of the first object is 30.5 Newton seconds at 65.9 degrees above the left vertical, or well, above the left horizontal. Okay, or to the left of the horizontal, right? Above, yeah, above the left horizontal. So what we know from Newton's third law, the impulse on object 2 should be equal and opposite, so we should get below 65.9 degrees below the right horizontal. But let's just confirm this, and if there's discrepancies and you do not get 30.5 as the magnitude and the 65.9 degrees below the horizontal on the right as the angle, then you know that something went wrong in your math. So it's a good check. If you feel confident in your math, you can just say delta P2. We can come in and write it, right? 30.95 Newton seconds at 65.9 degrees below the right horizontal. Because we know that Newton's third law says force is equal and opposite, so we should have a 12.45 that way, a 27.9 that way, and a 30.5, which is 65.9 below, because these, right, these two angles are 180 degrees, or sorry, these two are 180 degrees away from each other, and that's what we consider opposite in 3 dimensions. But I'm just going to show the math as we're doing it so that we can see that this does work out, and then you can trust yourself in time. So we're doing P2x is equal to M2 VFx 2 minus V naught x2. M2 was 7. Remember, the VF is that 6.91 because it's the same object as the first one, but the velocity initial was 5.14. And again, I found that from over here. So 6.91 minus 5.14 times 7. It's a pretty good sign. It's a little, we can take into account rounding, but delta P2 is equal to 12.39. which is positive, which is opposite of the delta px 1. And again, it's within rounding. If we were to hold on to a few more digits, they would get closer, but this rounds up to 12.4, close enough, Newton seconds. And then if we do the y, delta p2y, m2 v f y2 minus v naught y2, delta p2y is 7 vf 2.15 minus, right, 6.13. This is a good sign that we're going to get a negative value, as we know it should be opposite. 2.15 minus 6.13 times 7, 27.86. Hey, that's even closer and more spot on. Right, and we can confirm. I'm not going to do the math to confirm it, but I'm just gonna again show you. Right, we have a 12.39 Newton seconds. Right to the right, which is positive, we have a 27.86 Newton seconds, which is down, which again, opposite of what we had there. So if we were to draw this hypotenuse and solve this angle, we would get, as we predicted, 30.5 at 65.9 degrees below the right horizontal. Okay, and that's going to be true on our impulses, so you don't have to calculate both. Again, you can use it as a check, but if everything else is good, and you feel confident and you have checked over your other work, then your impulses are going to be equal and opposite, meaning